Hello everyone and welcome back to Metabolism. Today we're going to be talking about redox reactions or electron transfer reactions. Redox reactions are reactions that transfer electrons from one molecule to a different molecule. This is shown by this diagram here of molecule A, which has electrons to start with and ends without electrons, therefore making it oxidized, and molecule B, which starts without electrons and gains electrons for this reaction, making it reduced. Well, where do these electrons come from? It comes from the other molecule. So A is donating electrons to B through this redox reaction. So molecule A starts out with electrons and donates electrons, making it the reducing agent, whereas molecule B starts off without electrons and gains electrons at the end, taking them from molecule A, which makes it the oxidizing agent. It's facilitating the oxidation of the reaction A, whereas A is facilitating the reduction of the reaction B. You are being reduced by being reduced in charge. So that's a good way to remember what's occurring in these reactions. The way to measure the potential of a molecule to be reduced is through the reduction potential. This is E0 prime, going to show which molecules are most likely to be reduced or be oxidized. As you can see here at the top, this reaction is going to be very likely to proceed from left to right in a reduction reaction because the reduction potential is very high. However, as you go down, this reaction here at the bottom is going to be very unlikely to proceed from left to right. Reduction is going to be very unlikely to occur, and rather, the reaction is going to be more likely to proceed from right to left because it has a very low reduction potential. So it's very likely to be oxidized, whereas this reaction at the top here is very likely to be in the reduced form. The arrows here in this diagram show which molecules are most strong as reducing or oxidizing agents. So this molecule here at the very top is going to be a very strong oxidizing agent because it's very likely to be reduced, which means it's very likely to receive electrons. Whereas the molecules down here are very unlikely to be in this state. These molecules at the bottom here do not like to be in the state that they're in. They want to donate their electrons, and therefore they're very good reducing agents. So these half reactions that we looked at previously, they're just a really good way to understand what's going on in a full reaction. Both of these reactions are reduction reactions, reduction potential associated with each. The higher the reduction potential, once again, is indicative that it's more likely to reduce. So in this case, we're going to flip the bottom reaction because this reaction is less likely to occur as a reduction reaction because it is more likely for the top one to be reduced, so therefore the bottom one is going to be oxidized if they're combined together, which is what happens here when you combine them. You're going to have this first molecule, the silver molecule, is going to be reduced, whereas the copper molecule is going to be oxidized. NADH and NAD+ are two molecules that are a great example of electron carriers, as in these are molecules that can be reduced and oxidized and facilitate other reactions by donating or receiving electrons. Their reduction potential is negative 0.32, so therefore it's a little bit more likely to be oxidized. In your review, is NADH a reducing or an oxidizing agent? NADH is a reducing agent because it donates electrons. So remember, molecules that have more electrons are going to be the reducing agents because they're going to donate those electrons. And through donating electrons, they're going to become oxidized. So in this case, NADH becomes NAD+ and is donating electrons to another molecule as part of a different reaction. ATP is one of the most important molecules in the human body. When we eat food, we convert this food to energy through metabolic processes, and we store this energy as ATP to be used in other reactions throughout the human body. And ATP can be produced in two major ways. First way is through substrate level phosphorylation, a form of ATP production that is low yield. However, it's still very important. In this example here, this molecule, phosphoenolpyruvate, is a phosphorylated molecule that is converted to pyruvate through pyruvate kinase. The phosphate on the phosphoenolpyruvate is donated to the ADP, which becomes ATP through this reaction. ADP is the form of ATP with one less phosphate, whereas ATP is the fully phosphorylated and highest energy form of the molecule. So this is the form that we want to have in the body to facilitate other reactions. Fermentation is an example of a metabolic process with this substrate level phosphorylation occurring. Glycolysis is going to facilitate the production of ATP through 2-ADP to 2-ATP, and this is just going to be a substrate level phosphorylation, so a transfer of a phosphate group from one molecule to the ADP, making it into ATP. This is going to be part of glycolysis, whereas the rest of the fermentation is simply a way for the glycolysis to continually occur, and you're going to have the NAD plus and NADH, which are electron carriers involved in the glycolysis portion of the reaction. They're going to be replenished through the fermentation part of the reaction. So NAD plus is going to be receiving electrons from glycolysis here and become reduced, and then it's going to donate electrons in the fermentation part of the reaction and then be oxidized so it can be used again as part of glycolysis. However, this overall has a low ATP yield because the electron acceptor is carbon, which does not have a very high reduction potential. It doesn't want to receive electrons that badly, so it doesn't release a lot of energy when it gets to receive those electrons. Oxidative phosphorylation, on the other hand, is a very high ATP yield. Oxidative phosphorylation overall is facilitated by a proton gradient. Protons are pumped into an intermembrane space, and this higher positive charge in the intermembrane space wants to leave, so it's going to have a high potential energy. And the enzyme ATP synthase is going to convert this potential energy into potential energy in ATP. As protons pass through the molecule from the gradient outside of the outer membrane to the inner membrane, they are going to cause the production of ATP. This reaction, oxidative phosphorylation, like I said, will occur in mitochondria in the eukaryotes, right here in the intermembrane space. Prokaryotes and other organisms that do not have mitochondria, they're just simply going to occur in the membrane surrounding the cytoplasm. So the protons will be pumped out of that membrane. In a gram-negative bacteria, there are two membranes, so the protons will be pumped into an intermembrane space and then re-enter the cell. In a gram-positive bacteria, they'll be pumped into that space between the outer membrane and the peptidoglycan, and then they will come back into the cell, once again through ATP synthase. The electron transport chain is what facilitates the pumping of protons into this intermembrane space and facilitates the production of ATP by oxidative phosphorylation. So this ties back into reduction potentials. Each of these molecules involved in the electron transport chain has their own reduction potential. And as they pass electrons down the chain, they're going to get to a higher and higher reduction potential until they finally get to oxygen, which has a very, very high reduction potential. And by passing electrons down, they're allowing some protons to be pushed into the outer membrane space all the way down through this chain. So you're going to start with NADH dehydrogenase. This is a membrane-bound protein, and it binds NADH. It transfers 2 electrons and 2 protons to the flavoproteins, which receive those 2, and then transfer 2 electrons to the iron-sulfur proteins, which only carry electrons to the quinones. These are non-protein electron carriers, and they receive 2 electrons and 2 protons and transfer 2 electrons to the cytochromes, which carry and release 1 electron each, all the way down to oxygen. Mini review: does substrate-level phosphorylation or oxidative phosphorylation produce more ATP? Oxidative phosphorylation produces more ATP. It produces 32 to 34, just 2. 2 is produced by substrate-level phosphorylation, and oxidative phosphorylation has a much higher production of ATP because oxygen is a really good electron acceptor. It has a very high reduction potential, and this allows for a greater release of energy overall. Really appreciate you guys' time for these videos. Please let me know if you've enjoyed them, if you found them helpful, anything that I can do better in the future. I really would like to know. Let me know any other ideas you have about how I can improve these videos, like anything that would be more helpful to you, topics that you'd like me to cover, or anything like that would be awesome. So thank you so much for watching, and I hope you have a great day and happy studying.